relative isotopic mass. Okay, just as a reminder, an isotope are atoms of the same element which have different numbers of neutrons. Remember, they have the same amount of protons, so they've got the same atomic number, but they will have a different mass number. So if we have a look here at two examples, there's two isotopes here of chlorine. So you've got chlorine 35 and chlorine 37. Notice the atomic number for both is still 17, but the difference between the two is that chlorine 37 has 20 neutrons, whereas chlorine 35 only has 18 neutrons. Atoms are very, very, very small. Okay, and I love this diagram here, which says that if every person was the size of an atom, the entire human race would fit on the head of a pin and there'd be room left for billions more people. That's how small atoms are. Because they are so small, they have a very small mass. Carbon's mass is 2 times 10 to the negative 23 grams. That is 0.0000, all those zeros, 23 grams. It's tiny, really tiny. This creates a problem for chemists because it's difficult to measure and also it's difficult to use in calculations. So, chemists have come up with a solution for that. We don't need to know an element's exact mass, but what we do need to know is the mass relative to other elements. This is where we've come up with relative isotopic mass. Relative to other atoms, what is the isotopic mass of the isotope? So relative isotopic mass is the mass of one atom of that isotope, which is relative to the mass of one atom of carbon-12. And the mass of one atom of carbon-12 is given the amounts of 12 units. So that isotope of carbon is given the mass of 12 units exactly. So let's have a look at this diagrammatically. Here I've given you carbon, one carbon atom, and we'll say that that's carbon-12. So carbon-12, its actual mass is this 0.0000, so 2 by 10 to the negative 23 grams, but instead we've said that it's got a relative isotopic mass of 12 units. Okay, let's have a look at these here, and these are hydrogen atoms. To find the equivalent weight to one carbon atom, we need 12 hydrogen atoms to have the exact same weight. So we can now work out a mass of hydrogen relative to carbon-12. So hydrogen, which actually has a mass of this, is equal to 1/12 because there's 12 of these equivalent to one carbon. So it's got a relative isotopic mass of 1 unit. Let's have a look at a second example. So here I've taken one sodium atom and it's got the equivalent mass of 2 carbon atoms. Now, we know that one sodium atom is equivalent to 2 carbon atoms, and we know that carbon-12 has a relative isotopic mass of 12 units. So therefore, the mass of one sodium is double the size. So sodium will have a relative isotopic mass of 24 units. So we can now look at this relative mass of these different atoms. So lithium, we'll work out number of protons, number of neutrons, number of protons and neutrons. And if we look at the mass, which is obviously the number or the mass number or the number of protons and neutrons, it'll be 7 divided by 12 times 12, which is 7. And that's the mass of an atom relative to carbon-12. With carbon, obviously that's going to work out to 12 because carbon-12 equals 12. Everything else is relative to carbon-12. So, isotopic composition of some common elements, and this is taken from your textbook, and you'll see here that different isotopes have different isotopic masses, and it depends on how many neutrons they've got. But these figures here are worked out based on carbon-12 having exactly a mass of 12. Everything else has been calculated relative to carbon-12's mass. How do we find out the weight of different isotopes? We use a process called mass spectrometry. Okay, it's used to determine the relative isotopic mass of different isotopes. And it's this big machine that looks like this. That was actually from a few years ago. They've got smaller desk size ones now. But the process is something like this. And it looks a little complicated, but it's not at all. There's two main points to it. The first thing we already know is that ions are charged atoms, and these can be deflected by magnetic fields. What a mass spectrometer does is it has a look and it sees that lighter ions are deflected more. This makes sense. Heavier ions are deflected less. Okay, so let's look at it in detail. Stage 1 of mass spectroscopy involves ionization. We have to turn the atoms into ions, and this is where this happens, right at the front of the unit. The atom is formed into an ion by using electrons to knock off one or two electrons, okay, to make it a positive ion. And generally we're only trying to knock off one electron to make it a positive 1 ion. So here you can see there's an electron source. They fire these electrons into the sample and it knocks off electrons to give a positive ion. So now we've got a charged ion, and this stage is called ionization. The second stage is called acceleration. It's exactly what the name means. These particles are accelerated into this magnetic field. So they're just basically sped up so that they've all got the same amount of kinetic energy. So they're all travelling at the same speed. The third stage involves deflection, and this is this section here where the magnet is. Okay, it involves this entire section. This is the first bit with the magnet. And you've also got magnetic field across here, and this is going to cause deflection of the ions. And there's two major factors that influence the amount of deflection. One we've already discussed, which is the mass of the ion, and the second one is the charge of the ion. If the charge is greater, it's going to deflect more or attract more because it's got a higher charge. So let's have a look at the mass of the ion. Here we've got three different streams. So a mixed ion stream is coming into the mass spectrometer. You'll see that one ion A here is deflected the most and ion C is deflected the least. So these ones here are the lightest ions. These deflect the most, okay, because they're lighter, they weigh less, they have less mass. Whereas ion C are the heaviest ions, okay? These ones will not deflect as much. You need more energy to deflect those. The charge of the ion. So here's our mixed ion stream again. If these had different charges on them, the higher charge is deflected the most. So if we have a look, this one here is deflected the least, so it must be 1+ ions. The green one here are 2+ ions, and hypothetically the 3+ ions would be deflected the most because they've got the greatest amount of charge, okay? They're going to be attracted more to the electromagnet. Because there's two factors, the mass and the charge, which can be responsible for the bending or the deflection, okay, we come up with what's called the mass to charge ratio. And it's important that we consider both of these when we're trying to determine the mass of an isotope. So an example of what I'm talking about is if you've got an ion with a mass of 28 and a charge of 1 positive, okay, the mass to charge ratio would be 28. 28 divided by 1. If you've got an ion though with a mass of 56 and a charge of 2+, your mass to charge ratio is going to be 28 as well. So they're both going to deflect by the same amount, but the masses are different. So it's really important that we consider the charge of that ion when we're looking at trying to work out what the mass of that ion is. Most of the ions passing through a mass spectrometer though will have a charge of +1, which means that this isn't too much of a worry, but it's something that you need to remember and to take notice of because charge is important in the deflection through a mass spectrometer. And the last stage is detection. And this happens right at the end here. And basically they're detected electrically, and you get a wave pattern that looks something like this, or they call peaks. So a graph will come out and you'll have the relative isotopic mass on the bottom and you'll have the relative abundance in that sample on the side. So of course if you've got one type of atom in there, the relative abundance has to be 100%, okay? Because you've got isotopes of that element, okay? It can only equal 100%. So the addition of the amount of the different isotopes must come to a grand total of 100%. So in this sample here, we've got isotope 7 is 50% of the total of that atom. Isotope 9 is 30%, and the other 20% is made up of isotope H. So we've got 50 plus 30 plus 20, which equals a total of 100%. Let's have a look here at molybdenum. This is a mass spectrometry graph that's being drawn of the various isotopes. And you can see here that there's 7 different isotopes. 1, 2, 3, 4, 5, 6, 7. They have relative isotopic masses of 92, 94, 96, 98 and 100, okay? The most abundant ion has, or is, the 98 here, or the isotope with the relative isotopic mass of 98, okay? All of these abundances will add up to 100% of the total amount of molybdenum atoms of that isotope. So this short video just shows what we've been talking about.
The ion beam passes between 2 charged curved plates, which deflect it in a curve so that it enters the area here, where an electromagnet produces a vertical magnetic field. This further deflects the beam in an arc of a circle. On emerging from the magnetic field, the beam is deflected again by another set of charged plates which direct it into the detector. The amount of deflection by the magnetic field depends on the mass of the ion, strictly its mass to charge ratio, but the vast majority of ions have only a single charge. The deflection also depends on the strength of the field. Heavier ions will not be deflected sufficiently in the magnetic field to reach the detector. Lighter ions will be deflected too much. During a run, the magnetic field is gradually increased so that ions of successively greater mass enter the detector.
So, relative atomic mass. If we have a look at these relative abundances and their relative masses, we can then work out a relative atomic mass. Relative atomic mass is equal to the average relative isotopic mass of one atom. Okay, but it needs to take into account the abundance of that atom. And it's worked out with a formula like this. So, relative atomic mass equals the relative mass of isotope 1 times its percentage abundance plus the relative mass of isotope 2 times its abundance. That gets divided by 100. I'm going to show you an example. So let's look at oxygen. Oxygen has 3 naturally occurring isotopes, 16, 17, 18, and these are the exact relative isotopic masses of those isotopes. We need to consider the abundance of these in nature. So which one of these occurs more? If we have a look here, oxygen 16, 99.76, so the majority of oxygen is this particular isotope, isotope 16. However, there are small amounts of oxygen 17 and oxygen 18 that exist. 0.04% is oxygen 17 and 0.2% is oxygen 18. We have to take those into account when we're working out our relative atomic mass. So we use the formula. Isotope 1's relative mass times its percentage abundance. Isotopes 2's relative isotopic mass, which is 16.99, times percentage abundance, which is 0.04. And I've written them down here for you. Last one, isotope 3, we've got its relative mass, which is 17.999, multiplied by 0.20. So each isotope, you're just multiplying the relative abundance percentage by the relative isotopic mass. You add those together and divide the grand total by 100. So if it's got 5 isotopes, you'd work this out for the 5 isotopes. If it's only got 2 isotopes, you'd work that out for the 2 isotopes. So our answer is 16.0. 16.0. Does this look familiar? It should. When we look at the periodic table, the mass number of oxygen is 16.0. So the relative isotopic mass of an element is equal to the mass number on the periodic table. So let's have a look at a second example here. Natural chlorine consists of 2 naturally occurring isotopes, Cl35 and Cl37. And here they are on the mass spectrum graph. You can see 37 here has a percentage abundance of approximately 25% and 35 here of approximately 75%. If we read our question, we can see that. So the relative isotopic mass of Cl35, to be exact, is only 34.969. Okay, it's not exactly 35, it gets written as 35 though. Its percentage abundance is 75.91. The second, Cl37, has a relative isotopic mass of 36.967. Again, it's not quite 37, but we write it as isotope 37. Its abundance is 24.09. Abundance there, 24.09. You'll notice again that the overall abundance of 75.91 plus 24.09, the grand total there is 100%. It has to be, because there's only 2 isotopes occurring naturally. So it's asking you to calculate the relative atomic mass. So again, we use that same formula and we put in isotope 1, 34.969 is its relative isotopic mass multiplied by its percentage abundance, which is 75.91, plus isotope 2's relative isotopic mass, which is 36.966 times the abundance of 24.09. Divide all of that by 100 and you get 35.45. This number here is the relative isotopic mass of chlorine, and it is equal to the mass number of chlorine when we look at the periodic table. It now makes sense why this mass number is in decimal places. This is because it is an average of the percentage abundances of each of the naturally occurring isotopes. Question 1. I'd like you to pause the video here and I'd like you to have a go at this question, please, and I will run through the answer for this. So, lithium exists in 2 isotopic forms. So lithium-6, which has an abundance of 7.40%, and lithium-7, which has an abundance of 92.6%. The precise atomic masses of the 2 isotopes are 6.01512. So lithium 6 is actually 6.01512 and lithium 7 is 7.01600. Calculate the relative atomic mass. So we use the formula again. Lithium 6 relative mass is 6.01512 multiplied by its abundance, which is 7.40, plus lithium 7's details, so relative isotopic mass of 7.01600 times its percentage abundance, which is 92.6. Divide all of that by 100 and you get 6.94. Have a go at questions 2 and 3. I'm going to put the worked solutions to those right at the end of the video. So see how you go. If you're having troubles, you can fast forward to the end of the video, or you can have a look at those at the end. Okay. The other thing you were asked to do was sketch these on a graph. Now, when you're sketching them on a graph, it's important to notice, or to put at the bottom, the relative isotopic mass, which is just transcribed. So it's 6.01512 and 7.0160. And then you want to draw in some peaks. So we've got a 7.4% here, abundance, so you need a little tiny peak here for this one. And for the other one here, lithium 7, you've got a big peak, which is 92.6%. So you can actually draw a dotted line across there and a dotted line across there if you like to show the exact abundances. So you can now complete booklet questions 2 and 3, and you can also do chapter 4 question 1. What I've done is I've put the work solutions to the booklet questions 2 and 3 at the end of this video, so there's nothing else to watch unless you've had trouble with those questions, and then have a little look at the way I've worked through those solutions. Question 2. Copper consists of 2 isotopes, which is copper 63, which has a percentage abundance of 69.1%, and a relative atomic mass of 62.95, and the second isotope is copper 65 with a relative isotopic mass of 64.95. The question asks you to work out the relative atomic mass of copper. So we get our formula, which we know. Relative atomic mass equals isotope 1's relative mass times percentage abundance plus isotope 2's relative mass times percentage abundance, all divided by 100. We put those figures in. So isotope 1 is copper 63, which it has a relative atomic mass of 62.95 and a percentage abundance of 69.1. Second isotope is copper 65, which has a relative isotopic mass of 64.95, and the abundance we work out because one isotope has the abundance of 69.1. In total, they must equal 100, so the abundance of the second isotope must be 100 minus 69.1. Now we just need to solve for that. Remember when you put it into your calculator to put brackets around it or to work these out individually first. So we get an answer of 63.6. It asks you to graph this mass spectrum. So make sure you've got your relative isotopic mass on your x-axis and your relative abundance on your y. And then you just need to plot the points. So it's 62.95, which is the first isotope, has a relative abundance of 69.1, which is approximately up to here. And the second isotope here has an abundance of 30.4. And that's been written in there to make it clear. You could also write it on the y-axis there. Question 3. Use this data to determine magnesium's approximate relative atomic mass. All the information's here. This is isotope 1 with its relative isotopic mass and percentage abundance. So we pop all of this into the equation. So isotope 1 is 23.9, 78.7, plus isotope 2, 24.99, times its abundance, which is 10.13. Isotope 3 is 25.98, multiplied by 11.17. All of that divided by 100. Again, remember to work out your multiplication in brackets first, and you'll get an answer of 24.31. To graph this, you just need to draw those peaks in as we've done before. So these are the peaks drawn in here. Remember, your relative isotopic mass is on your x-axis, your relative abundance is on your y-axis. I've put about 10% here because these are 10 and 11% respectively, these two peaks, and 80% here. To be more clear, you might choose to write them on the actual graph themselves or on the axes here. These are written in here, magnesium 24, magnesium 25 and magnesium 26. Again, to be more clear, you can write these in the bottom axes on the x-axis here.